This is the 33rd lecture on a course on single agent heuristic search. And we're continuing with looking at inconsistent heuristics in this lecture, or in this video. This video is going to look at one piece that we can use as a tool that will get us to an algorithm that can handle inconsistency with running time better than O of n squared. And so what we're going to look at here is we're going to look at some properties of what is going on in search with an inconsistent heuristic and what makes this problem perhaps more tractable in practice. And so we're going to be looking primarily at an algorithm called breadth first IDA star, or a variance of that. And this algorithm was invented by Rong Zhou and Eric Hansen in, I think it was around 2004. And so we're going to see how we can take that and we can modify it to work for our purposes. So yeah, this is Zhou and Hansen, 2004. And I'm going to start with actually a little bit of background of what's going on when we think about inconsistency. And so let's look at inconsistency over here. And then we'll come back to this algorithm. In inconsistency, what we saw, if we looked at an algorithm like algorithm B, what algorithm B does is it ignores the heuristic values in the re-expansion phase, because we have this property that if we ignore the heuristics, we're able to avoid re-expansions or mini re-expansions. Because the idea is it's the heuristic, and particularly the inconsistency in the heuristic, that is causing our poor performance. But it only does it partially, right? It's still guided by the heuristic as it searches. And so what we would see, for instance, if you were just to take a problem in general, is that using Dijkstra's algorithm or uniform cost search. So Dijkstra's algorithm or uniform cost search will never do node re-expansions on a graph with positive edge costs. And the problems that we're looking at we have our heuristics and we have our edge costs are all positive. And so if we were just to ignore all the heuristics, then we would search the state space, we'd never do re-expansions, and we would be done. And so that seems really good, except that maybe the heuristic is really informative, right? And so the thing is that we want to use the informative information from our heuristic. Can be informative. And so we have this tension of like, I want to use the heuristic because it's informative, or maybe it's informative in many places in the state space. But Dijkstra's algorithm is able to avoid the re-expansion problem. And so that's going to bring us to this algorithm, BFIDA star. And BFIDA star, and we're going to use it, it's a general principle. That's a very interesting principle that has to do with this question of how do I guide my search? So sometimes people might describe A star as, well, A star isn't guided by the heuristics, but it just uses them to prune states out. And I think that's an inaccurate description of A star, because A star really is guided by the heuristic. It uses the F cost, which is G plus H to guide the search. And what we're going to get with breadth first IDA star, or in general, this breadth first approach, is we're going to use another way of doing our search. So it could be IDA star. It really could be anything else sitting at the bottom, but we're going to use basically a breadth first search to search here. And then we're going to use our heuristics in a different way. Okay. And so this is the idea. Is we're going to, basically we're going to say, given a cost bound, let's just call that B. Okay, so given a cost bound, what we want to do is we want to expand, we want to do a search. And as I said, this could be an IDA star search, it could be some other search, but we're gonna search. And we're going to order expansions by G, low to high. So this is going to be a breadth first search. And so we've got a cost bound B. We're going to order expansions, and we're going to prune states with F greater than our bound. Okay. And so the idea here is that now we're going to order our search by G cost, going from low to high. And what we're going to do is we're going to use our heuristic, that is our F cost, which is G plus H, only for pruning states that have gone outside of our bound. And Joe and Hansen, when they did this, they were motivated by problems that looked like this. So very often the A star frontier can look like this, where we have a start, our goal is going to be here. And what happens is if we do an A star search, the A star search sort of looks like this frontier. So we might expand some little frontier here, and then we do some frontier here. And I'm going to make this be a little bit smaller just for the sake of being able to draw this out. But the idea is, you've got some first layer here that we're going to do. We have some second layer here that we do in between. And then we're going to have a third layer. And that third layer, is going to be slightly bigger here. Okay, so this gives us our layers of our search. And if you look at an observation here, what you see is that the open list, which is sort of each, so like the blue layer could be an open list. The green layer is going to be essentially the open list for the yellow layer. And then you continue to have layers outside of here. This open list is very large. It sort of spans the entire state space. But there's an alternate of what we could do here. So the reason is basically we've got these states with high heuristic and low G cost. We have states with high G cost and lower heuristic. And so we get this broad range of states here, and our open list is very big. Okay, what we're going to do is we're going to think about doing a breadth first search inside the space where we're going to prune the space based on the heuristic value being outside of F. And when we do that, what's going to happen here, I'll do this in red, is our search is going to go out in a breadth first order. So our search is going to go out here, and what's going to happen is we get to this border, we're going to start pruning states off. So right here, we prune states off, but everything inside here is within the bound. And so if I continue this search, what we see is that the search is going to continue like this through the state space in a very different ordering of states. And in particular, what we see is the number of nodes that are on the open list in one time is this small slice of the state space compared to what I would see in a A-star search, where I get these big, long slices here. And so what Joe and Hansen were looking at is that, look, we can be much more effective in our search if instead of ordering our states and getting these big, long open lists here, this big, long search, we're going to try and do things here where I'm going to get these smaller layers in our search like this. Okay, and so the idea here is actually going to give us a key idea that we'll then use, and we'll put it into the next video. So as I said, we're going to keep this video relatively short. But the idea that we're going to get here is that imagine that I had a oracle that we knew C star, the solution cost. Then what we could do is we could just say run, and I'm going to call this breadth first uniform cost search with a limit of C star. And what would happen here? Even if I have an inconsistent heuristic, it doesn't matter, because what's going to happen is we will prune away anything that's not a necessary expansion, and the states that are remaining inside here, we'll expand them from low to high G cost. Because we're going from low to high G cost, we'll never do node re-expansions, and we would be able to search directly from the start to the goal. And as we go directly from the start to the goal, we would do every node exactly once. As I said, there's no negative edge costs in here, so we can't be misled by the heuristic, but we can be pruned by the heuristic. The heuristic can prune off what we're doing right here. So what this says is that we have this potential that if I knew the optimal solution, then I could use a breadth first oriented search, maybe not IDA star, but a breadth first uniform cost search, and it would be able to search my state space efficiently. And so again, what we're going to do basically is we're just going to do a best first search, and we're going to order by G-cost low to high, with the exception that we prune states with F greater than equal to B. Okay. And just to see here, just to reiterate one time, if I just do a regular A star, I'm ordered by these colors here. And I have many states around here. If I'm not ordered by this, I'm going to be ordered by these red states here. The important fact, though, in fact, we don't care about whether these are large or small in practice for an inconsistent heuristic. What we care about is whether we stay inside the nodes that we need to expand, which we do by pruning anything that has F greater than B. So that's one thing we care about. And the other thing we care about is node expansions. And because we're doing a uniform cost search inside here, we'll never have to do notary expansions. We're basically entirely throwing away the heuristic and only use the heuristic as a tool to prune the outside of the state space. Okay, so this is a tool that we could use that says I can use this breadth first uniform cost search. And if I use this and I, for instance, knew what C star was, then I would just run this one time with C star. I would exactly solve the problem, doing exactly the necessary node expansions, and I wouldn't see any of the n squared overhead that we've been seeing with inconsistent heuristics. So what we'd like to do, in the same way that we did for budgeted tree search, what we'd like to do is turn this breadth first search into an oracle that will allow us, or use it along with an oracle that will allow us to solve these problems without having to do too many node re-expansions. And so we will, in the next lecture, we'll look at how that can be done.